Section 10.5, angle relationships in circles. Okay. If you do not have highlighters and a ruler, please pause the video and go with them now. All right, now that you have all the tools that you need, today we're going to be talking about angle and arc measures and how they relate to different types of lines that intersect inside, outside, or on a circle. Okay. So our first theorem is the tangent and intersected chord theorem. So I have a tangent and a chord. Okay. So here if I have a tangent and a chord that intersect at a point. So here they intersect at a point. This point right here is point A right there. Okay. Intersect at point A. Okay. Then the measure of each angle formed. So we're looking at the measure of this angle. So we have this whole angle. Angle 1, again, it goes from tangent to chord. That angle 1, the measure of each angle formed is half the measure of the intercepted arc. So here, angle 1 is going to be half of this arc, half of the arc from A to B. So whatever the measure of that arc is from A to B, again, that measure is measured by the central angle measure. So whatever the measure of that arc is, that angle there 1 is going to be half of that. And the same with measure of angle 2. So this other angle here, this angle 2 here is going to be half of this angle measure there. Okay. So to use that, here in extra example 1, here line M is tangent to the circle. So we know this line here is tangent to the circle. We want to find the measure of the red angle. The red angle, you can't see it. The red angle is this one right here. So we want to find the measure of this red angle right there. Okay. Well, I know here its intercepted arc is 240, so the measure of angle 1 is going to be half of that 240. So the measure of angle 1 will be 120 degrees. And I'll always double check, does it make sense based on the picture? Sure, it makes sense that would be 120 because it doesn't look straight up and down like a 90, so it's bigger than 90, so 120 degrees makes sense. So now here for extra example 2, we want to find the measure of the red angle or arc. The red arc in this case is this big one that goes around this way. Sorry, it didn't get printed in color. This is the red one right there. So we're looking at, if we look at this angle, they give us that 155. That 155 is that angle right there between the chord, okay, and the tangent. So I know the measure of this angle, the measure of that angle, I don't know, we'll call this angle 1. The measure of angle 1 has to be half the measure of that arc, and that would be the arc from L to J to K. So it would be half the measure of the arc L to J to K, that arc. So then I know I'm trying to find the measure of that arc, so I'd have to multiply both sides by the 2 to get rid of that 1/2. So the measure of that arc, the measure of arc LJK, then would be equal twice of 155, 2 times 155, which 2 times 155 is 310 degrees. Now, does that make sense? Well, sure, all the way around is 360. We're all the way around except for that little piece, so 310 does make sense. Okay. All right, next part, intersecting lines and circles. Okay. So if I have intersecting lines, so if I'm going to have 2 lines intersecting, so I'm going to have one line here, and we'll do another line like this. So if I have 2 lines intersecting, so there's my 2 lines that are intersecting, and they're intersecting in and around a circle, okay? There's really 3 different ways they could intersect. They could intersect on the circle. So the intersection could be on the circle. Like if that's my intersection point right there, my 2 lines then could look like this. They could intersect on the circle, like that. Again, the intersection could be any place, but it's located on the circle. It could be in the circle. So my intersection point could be right here, and then I'd have, let's say, a line like that and a line like this. So that intersection point could be in the circle. So we could be on the circle, in the circle, or you guessed it, this last one, outside the circle. So they could intersect. My intersection point could be out here. So then I'd have one line and So depending on where they intersect, we have a couple different theorems for that. So our first one is angles inside a circle theorem. So this is if we have two chords or lines that intersect inside a circle. So this deals with this in a circle. So this one is our in a circle. Okay. So if they intersect in a circle, and you see here then, if we intersect inside the circle, we've got some vertical angles here. We also have some intercepted arcs. We've got an intercepted arc here, and then we've got this one here, and then we've got we've got a major one depending on how they intercept. But if two chords intersect inside a circle, then the measure of each angle is 1/2. So the measure of each angle. So the measure of, let's say, so again, here's my situation. I have two chords intersecting inside the circle here. So the measure of each angle, let's say I was talking about angle 1, it's half the sum. I always like to think of it, here they go, 1/2 the sum. Well, that's just a fancy way of saying the average. Sorry, over here. It's the average of the measures of the arc intercepted by its angle and its vertical angle. I always like to think the arc in front and behind. I'll show you what I mean by that here in this picture. So here, if I'm looking for the measure of angle 1, it's going to be half the measure of the arc here intercepted directly in front and the sum of those two. So if I take those two DC, there's arc DC and AB, the one directly in front and the one directly behind. So I average those two things. I find that arc, and I average them, and it will give me the measure of this angle 1 inside there. Okay. So here, if I'm looking for angle 2, let's change color, we'll go blue. Angle 2 here, if I'm looking for the measure of angle 2, I would need to average this one and this one to get to it. So I would need to average the arc again in front and behind. So we average them. So again, measure of arc AD and BC. So we add them together and we average them. That's if, again, we intersect inside. Okay. If we intersect inside, that's how we find those angles in there. Okay. If they intersect outside, okay, so if they intersect outside a circle, so that's a different color. So if we have an intersection outside of a circle, so that would be this situation right here. If we intersect outside of the circle, there's really three different scenarios if we're going to touch the circle. So we could intersect outside and one tangent and one secant. Okay, I could intersect outside and they both be tangent. I could intersect outside and they both be secant. Or there's one last scenario here. We could intersect outside and it not touch at all. If that's the case, then there's really nothing I can say about any of the angles in relationship to the circle because it just happens to be a circle floating around inside or outside of an angle. Okay, so this is our last scenario, but this theorem doesn't apply there because there's no intersection points for me to use. Okay, so if it intersects outside of the circle, here instead of adding, on this one we added the two pieces and took half of it. So we averaged it, we added and took half. In this case, we're still going to have that whole half idea. Do you see here? All of these have that half idea. But now what I do instead is I take basically the bigger arc. So there's my bigger arc. And then we subtract the smaller one, the one inside. Okay. So really, all three of these, you do the same thing. So I take the bigger arc, this one here, and subtract the smaller one, this one here, and you take half, okay? Again here, we take the farther away one and the closer one, because the closer one will always be, and we take half. And that will give us the measure of this little angle out here. Okay, so again, we just take the farther away arc, the farther away intercepted arc, and the closer one, we take those difference. Again, that difference, it's always positive because you always take the bigger one minus the smaller one. And then you take half. So 1/2 the difference of the intercepted arcs. Okay. Alrighty. Okay. So let's go ahead and let's look here for extra example 2. First thing I have to decide, do they intersect inside or outside the circle? Well, here are my intersections right there. That's inside. Okay. They intersect inside the circle. So now I know that it's going to be the average. Okay. So now we have to look at what we know. Here I know the measure of this arc is 80 degrees. And we're trying to find the measure of this blue arc here. Well, if you look, that would be the front and the back of this angle in here. But I don't know that angle. Okay. But this is when we have to use our previous knowledge. I know this angle here. I know this angle here is 94. Those are adjacent angles, so they'd have to be supplementary. So to get that missing angle in there, I'd have to take the 180 minus the 94, and I get 86. So this angle here is 86 degrees. So the measure of this angle here, this 86 degree angle, is the average of these two. So that 86 degree angle is half the sum of the other two. 86 equals 1/2 the sum of 80 plus x. So then now we solve. I could distribute the 1/2 in, but I think I'm going to divide both sides by 2 first. So I don't have to distribute that in. So I get 172 equals, the 2 times 1/2 is 180 plus x. Subtract the 80, and we get 92. So this angle is 92 degrees. To double check it, let's average those and make sure I get 86. So we're going to check it quick. So if I take 92 and add it to 80 and divide it by 2, I get 86. Yep, so all I did, can see, I took the average, or 1/2, here we can write it as 1/2, times 80 plus 92, and we get 86, so it did work. Okay, so x is 92. Okay, all right, this next one. Okay, here this intersects, this is outside, so that tells me I need to subtract the 2 arcs to get that outside angle. So this outside angle, they tell me that is 35. Well, to get to that, I take half of the difference of these. So we would write that equation, 35 is equal to half the difference of, this is going to be the bigger one, so 100 minus x. Okay. So we're going to multiply both sides by the 2 again to get rid of the half. 35 times 2 is 70. And then I'm going to subtract the 100 from both sides. Subtract 100. So that gives me negative 30 equals negative x. Divide both sides by the -1. X is 30. Again, let's double check it. If I take half times the difference, 100 minus 30, we get 35. It worked. All right, circumscribed angle. So first of all, I talk about what a circumscribed angle is. A circumscribed angle is basically just an angle with sides tangent to a circle. Okay. So a circumscribed angle is basically, I have an angle, let's say this is my vertex here. Okay, this angle needs to just barely touch both sides of this circle, and it is what we call a circumscribed angle because it goes on the outside, okay, of that circle. So it's a circumscribed angle. Okay, so we actually have a circumscribed angle theorem. If I'm looking for the measure of this angle in here, if I want to know what that measure is, the measure of a circumscribed angle is equal to 180 minus the measure of the central angle that intercepts the same arc. So the central angle that intercepts the same arc, meaning if this is a point of tangency, this is a point of tangency. My intercepted arc is right here. So I would just need to take 180 minus that central angle. So this angle right here. So whatever this angle is, this angle here would be 180 minus that. So the measure of a circumscribed angle, so the measure of, again, this angle here, D, is equal to 180 minus the measure of angle ACB. So take 180 minus this angle here, and it gives me that one there. Okay. So here, or basically we say what? Those two angles are supplementary, right? 180 minus the other. So if we want to find this value of x here, this value of x is equal to 180 minus that central angle. Well, they give that to you. 180 minus the 124.56. Yep. So this angle here is a 56-degree angle. Okay. All right, this next one. Find the value of x. Okay. Be careful. Word of caution on this one. This guy, this angle ACB, if we look at this angle here, not a central angle. It's an inscribed. Not a central angle. Caution. It's not a central angle. So I need to find that central. I need to figure out what that central angle would be, and I can actually use it to find that. So I'm going to go ahead and I'm going to draw in the central angle that goes from O to A, from O to B. Because I know here, I know this angle out here is 42, so this one would have to be 180 minus 42 for me to take 180 minus that. So this angle, the measure of angle AOB, would be 180 minus 42, which is 138 degrees. Because if I take 180 minus 138, I get back to the 42. So this angle is 138 degrees, which then also means that this arc, that arc is 138 degrees. And if you remember from a previous lesson, if we flip back in our notes, an inscribed angle, right there, that inscribed angle is half of the measure of the intercepted arc. So if this arc's 138, then this angle x is going to be half of that. So x is going to be half of the 138. So if we go half of 138, 138 divided by 2, and that gives us 69. 69 degrees. So we actually had to use two different theorems here. X there is 69 degrees. All right, okay, that's as far as we're going today. I don't want this video to get any longer. Example 4 was just one if we had time. Okay, so now you can go ahead and do your practice.